All right, good afternoon. Thank you for coming. My name is Don McWilliams. With the City of Bellevue, I'll be your moderator today. Today we have Brandon Steets, is that correct? With us from Geosyntec. Brandon's been with Geosyntec for 20 years, and he's going to talk to us today about PFAS in the stormwater.
All right, thanks, Don. All right, I know that 6-ppdq is your favorite constituent here in Washington, coming up from our California practice, and I'm going to talk about PFAS. I want to go to a slide that I actually had in my extras, but to start with, to put in context where these various constituents of emergent concern lie relative to one another. And so what I have here is this informal comparison, but it's speaking to the state of the science for three of the more high profile of the constituents of emergent concern. So we see PFAS, 6-ppdq, and microplastics. So going down, I have a list of some key questions of where they lie. One, standard methods. We should understand PFAS has a final standard method. 6-ppdq has a draft. Microplastics doesn't have one yet. Monitoring required in NPDES permits across the country. Yes, that's emerging, that's growing to be true for PFAS. That is only in the state of Washington, 6-ppdq, and it's not in permits for microplastics yet. Are there water quality promulgated, water quality criteria promulgated for them yet? Yes, for PFAS. Yes, for 6-ppdq, only in Washington. EPA only has non-enforceable screening levels. And then for microplastics, no, there are none so far. There are some 303D screening levels that are used for assessment purposes, and that's it. It may be only in California. Are there ambient levels in urban receiving waters that are above those criteria? Well, we don't know for microplastics. Yes, definitively for PFAS. For 6-ppdq, it's variable. The data is highly Washington-based, and there are not really broadly applicable water quality criteria yet. There's COHO criteria that are very low, but for other less sensitive species, we don't find that answer to be yes consistently. Then how treatable are they by standard green infrastructure? In comparison, PFAS is much, much less treatable. I'll speak about that. 6-ppdq, we've seen over and over that biofiltration, media filtration, infiltration. It's also true for microplastics in the academic literature. These are highly treatable constituents. As you'd expect, 6-ppdq is probably has a higher log KOC than any of the PFAS in the 5,000 plus range, or at least at the highest end of them. And then is it being addressed by product phase outs, true source control, legislation, and regulation? Yes, that's happening for PFAS, but it's a forever chemical, so it'll remain on the land surface for a while. 6-ppdq, very much so, right? You know better than I do about the extensive levels of effort working with tire manufacturers and the chemical manufacturing industry to replace PPD. With microplastics, that's probably not going to be possible, not in my lifetime. So very important to understand the relative state of the science and of the regulations for these three different important emerging constituents. Okay, so now going into the regulation of this contaminant first. I do a lot of litigation, so I apologize if I get kind of into the weeds on the regs, but I'll talk about stormwater permits for municipal, industrial, and then contaminated sites. This will be a nationwide perspective. It will not hone in on Washington State. So municipal stormwater systems, these are receivers, but they're still responsible for their airflow and quality. There's tons of litigation and enforcement bearing that out. PFAS monitoring is not incorporated into MS4 permits around the country anywhere that I'm aware of, but regional monitoring programs are filling that gap. PFAS limits are they're not in MS4 permits, obviously, right? You don't use numeric limits in general in the MS4 permit writing context. You use a BMP-based standard, which is the maximum extent practicable and minimum control measures. Numeric limits are occasionally appearing in MS4 permits. They've been in California for 15 plus years, and that's where you have TMDLs. So that process could develop PFAS limits in MS4 permits, but the 3D listing TMDL development process is usually decades, so it would presumably follow a similar timeline. The regulatory and litigation risks. Now, enforcement is rarely over receiving water limits. Right? There's receiving water limits shall not cause or contribute to water quality standard exceedances in the receiving water. That's pervasive in all MS4 permits and all stormwater permits in general. That's usually not enforced against. It's very, very rare. The San Francisco case that went to the Supreme Court was one of those. And but citizen suit litigations all the time pop up over that, grounded on that noncompliance around that provision in the permit. So this is now this decision from the Supreme Court is now altering that language in these permits to come out and look a different way, which has implications on the litigation list. Okay, and let's talk about what levels of what I have here is PFOS. So one of the sentinel compounds, it's one of the most ubiquitously detected in the urban environment. And I have log scale on the left, and I'm showing different publications with min and max values. And I'm showing 3 different criteria here. So what I'm showing from top to bottom are, at the top, you have EPA's draft chronic aquatic life criteria. I think a lot of people don't realize it's extremely high. This is unlike 6-PBDQ. This is not something that's acutely toxic to ecological receptors. This is the aquatic life ESL that's used in California, a preliminary screening level value. It's not enforceable. That's 75. Here we have the EPA MCL, the 4. It's remaining even under the new administration. And then we have the California human health criteria for consumption of organisms, which is consistent with the EPA number as well. It's way below, over 2, almost 3 log below detection limits. So this will put in context, what are the levels that you see in urban runoff? You know, for 6-PBDQ, you detected it in urban runoff, often above sensitive risk-based thresholds, so it matters to you. Well, for PFAS, understand that it's not a threat to aquatic life, it's a threat to human health through a drinking water pathway. And eventually, as criteria emerge, through a fish consumption pathway like dioxins, like PCBs and other bioaccumulative compounds. So it matters in urban stormwater. The latest data sets that I think are most relevant in the Bay Area, SFEI is generating this. And I think that this is a robust statistic representing the abundance of data. We have some other data sets showing that where you lack urban development, concentrations are below drinking water standards. But as soon as you add a small amount of residential development, just exposed sources on paints and roofs and everything else, you jump above that threshold. So it's a human health problem. This is also shown when we're screening CECs, constituents of emerging concern, in urban stormwater databases. This is a database we developed for the State Water Board of California, and we look at a broad swath of emerging constituents. This is a database that didn't have a field for 6-PBDQ yet, so 6-PBDQ is not in this data set. But we screened concentrations in our various data sets against risk-based thresholds for first ecological receptors and then human health for drinking water. And what popped out is that the pesticides and the phthalates drive all the ecological risk from stormwater discharges. PFAS have none. For drinking water, it's drinkable. For constituents of emerging concern, you obviously have pathogens. But for PFAS, it is not. So PFAS controls the human health risk from urban stormwater discharges. And it alone controls that amongst the constituents of emerging concern. So it's an important one. I guess one way you might look at 6-PBDQ is it's adding to this toxic stew of things that are already threatening to aquatic life. Whereas, this is why when we write drywall standards, we were saying that generally it's safe to infiltrate to drinking water, groundwater that's used for drinking water. Well, PFAS really changes the dynamic there. Okay, continuing on the applicable regs in the municipal stormwater permit, you have green infrastructure. If you're going to design it for PFAS, it requires significant carbon amendment, significant contact time control. All that translates to cost. What is the ultimate solution? You get that asked all the time. It's got to be true source control. There's an abundance of legislation that's flying out amongst the states right now, and that will phase it out from consumer products as well as outdoor products. The outdoor products obviously matter a lot more to stormwater exposure. There's a conceptual model being developed now by the San Francisco Estuary Institute, which is going to sort of semi-quantitatively evaluate this and then run scenarios for what happens when you phase these out to stormwater concentrations, which should be really interesting. And stormwater infiltration projects, I think that represents another risk of enforcement and maybe more importantly, some citizen suit risk, because PFAS has the perfect storm of attributes, which is it is toxic to human health. It is abundant at levels above toxicity thresholds. It is mobile through porous media, and it is persistent, right? I can't think of another pollutant that in stormwater that has all 4 of those attributes definitively. And so the recommendation here is to really, if you're doing like regional scale infiltration of urban stormwater, you might consider more robust pre-treatment in light of this, especially for dry wells where you're kind of pushing it under pressure closer to the water table. So standard green infrastructure, you heard me say it's generally not effective for PFAS chemicals across the board. They, just so you know, their KOC is generally like log 2 or less. So 1 is like it's completely hydrophilic. And this data bears it out. So this is a number of DOE bases where we just have background concentrations coming in blue, and then all the effluent concentrations in orange. And every one of these, like, these are a blend of some proprietary devices, some non-proprietary devices. I think all of them have media mixtures that have some component of GAC to them. I don't know that any have robust contact time controls, but in equals out. And that's what you expect for this chemical. Let's talk about industrial permits. So industrial permits, stormwater at most of these sites are going to be kind of at or around that urban background level, that like less than 100 nanogram per liter level. These permits, I would say Washington is a bit of an exception in this regard, but the federal regs and almost every other state builds these to solely regulate industrial sources, which are specifically defined in the regs. And so industrial permittees are not, again, Washington has some deviation from this, but they're not in the other states broadly responsible for pollutants like MS4s are. Now, okay, how's PFAS intersecting with these? What you're seeing is the first front end of ISGPs across the United States adding PFAS monitoring. It began with Colorado, Washington, and Minnesota as the first 3. It is applicable to specific industries. I think Washington might be one of the few that adds fuel terminals. The others focus on air transportation, waste management, a couple other industries. There are no limits or benchmarks yet for it. This is also true of the EPA multi-sector general permit, the draft that came out under the last administration. And there are occasional some source control BMP based requirements that are pretty doable. And then California has another element that's a pollutant source assessment that is discharger led that could add PFAS arguably. Continuing with PFAS and industrial permits, there's another class of industrial stormwater permits that are individual permits, right, for sites that are sufficiently complex. Those are what you're seeing across the country is increasing use of PFAS limits in individual industrial stormwater permits for PFAS associated industries, like the ones that I just listed. And so these manufacturing sites, there's at least 3 that I'm listing here that we've worked with: refineries, airports, individual permits that have PFAS limits in them. So those are already in existence. There's more expected to follow that trend. Those use a mix of water quality-based effluent limits that are based on water quality standards and technology-based effluent limits that are based on technological performance for removal of PFAS. And then there's dilution. I would say that dilution is a little less accessible for PFAS because the background concentrations are so close to standards. So you lack the assimilative capacity to support a dilution request. Citizen sue risks are really high there because of at least as long as the receiving water limit provisions remain in there. And you may say, well, what if I don't sample? Other parties are known to sample. And then before treatment, I would say, I often get asked, like, what are some low-hanging fruit that I can do if I'm this kind of site and I'm having to monitor for PFAS? I would say, in California and in almost every other state, the IGPs allow non-industrial source demonstration. So to the extent that your regulator may be open to that, that is certainly a possibility with the data sets that I cited in the earlier slide, showing what background levels are in urban stormwater, where there's non-industrial contributions there. And then I would say exposure prevention is critical. If you lack any exposure of PFAS containing materials and rainwater or stormwater, then you have a very good case that everything is, all the PFAS that's measured is not industrial. I have a set of slides on remedial strategies for PFAS impacted sites. These are sites that formally used and possibly released AFFF. I'm not going to go into detail here because I don't think that that's the general interest of this group, but I could talk about it later. I will just say in general, the lessons learned from working on a number of these across the United States is that the stormwater migration pathway for PFAS at such sites that are, you might call them acutely contaminated, is fast, especially in the understanding, the conceptual site model perspective of remediation engineers and scientists. It moves much faster than obviously groundwater. And so there's less time to do things like lengthy characterization studies and remedial planning. You often need to hop on it. It's significant as a mass flux relative to other migration pathways because the concentrations tend to be high in stormwater, and the volume of water is very high. It is long lasting, obviously forever chemicals. And there's a number of studies. This is one by Queensland. They've done a ton. We're working with them on research for DOD. And this leaching, it doesn't like wash out after a year or two. It continues for decades and decades. It's sticky, so it may contaminate your downstream conveyances. So where you had asphalt that had an AFFF release, now what's contaminated is the catch basins and the pipe work and everything downstream to the receiving water. When you're managing it through treatment systems, it's a non-steady flow. I think that kind of explodes minds of some wastewater treatment engineers. They're used to working with like a waste stream that is continuous and steady where their membranes are kept wet. So that's something that requires some additional thinking, but it is treatable through mass transfer technologies. That means ion exchange and GAC. Destruction, though, is still unproven at a field scale. This is an example of an active treatment system where for stormwater, PFAS, where we have really high concentrations coming in, we knock it down a log with GAC, and then we knock it down 2 more log with ion exchange. And so the net total is about 4 log reduction. It's consistently achieved. 100% of our effluent has been, for 4 or 5 years of operation, has been below our 75 threshold for ecological receptors. So how am I doing on time? Oh, thank you. It helps to talk fast. What I'll talk about now is that, I see a lot of presentations on guidance for stormwater media filters designs and stormwater control measure designs. And here's another one. I'm sorry, there's so many out there and tools to support that. This one is specifically built for DOD through the CERTIP research funding program using black carbon, which just means biochar and GAC for targeting trace hydrophilic organic compounds in stormwater. So they looked at a corrosion inhibitor, some current use pesticides, and 2 PFAS, PFOS and PFOA that are very hydrophilic. So very dilute in dissolved form, very difficult to treat, like your dissolved metals and orthophosphate. So this is a technical guidance manual. You can find it. I think if you use this QR code, you can go to you can also just Google ER18 1145, which is the CERTIP project number. And it talks about black carbon stormwater media filters. That's the acronym I'm using here. It talks about how to design them to achieve certain levels of removal in stormwater, and there's a cost element to predict the maintenance costs and the maintenance life cycle of these. So this is the guidance manual to do designs for PFAS removal using passive treatment systems. I will say that I get asked, do you prefer passive or do you recommend to your clients passive or active treatment for PFAS? And I say, well, it generally depends. If you have concentrations that are high, like at acutely contaminated sites, let's say concentrations where you need a log reduction or more than a log reduction, it's generally more efficient to go with active treatment, where we have pressurized vessels with GAC and things like that, whereas passive media filters are not really as well designed for frequent change out. I mean, imagine like this big footprint biofilter or an unvegetated media filter, and you need to replace it, let's say, every year. Like that would be a pain in the butt, right? To dig that whole thing out. Whereas, you can just exchange a GAC vessel pretty efficiently. It's built for that. The second part of this project was to produce this tool. It is this kind of like flexible Excel interface that is in the back end, hidden from you, is the removal isotherms that were developed in Stanford's laboratory using their column test, looking at PFAS removal at different influent concentrations, at different dissolved organic carbon concentrations, and all the other variables that dictate removal and the longevity of that removal, which is a real focus of the study and something that I've appreciated seeing in some of the other studies up here on media filters, where it's not just like how much did it remove in the first year, but it's how long will that removal rate remain and when do you need to initiate major maintenance to resuscitate it. So the next thing is, so you plug in these various inputs and you get contaminant removal and media filter lifetime. So here's an example where a scenario where, you say, well, I want to compare biochar, and this is I'm using here a regenerated activated carbon. Same hydrologic inputs, sizing criteria, you can have 85th percentile sizing or whatever you want. The same hydraulic retention time. I've got an influent concentration that is about 100 nanograms per liter, and let's say I want to achieve 5 nanograms per liter in the effluent. So 95% removal, just keeping it simple. And what it tells you is that, okay, you want 20% media content by volume. We want, in this case, targeting a time this is pretty long. I mean, by stormwater design standards, we tend to try, I try to keep it 45 minutes or less. And I don't know if some people go longer than that. I think the footprint really grows if you're going longer than that. But this is a long one. It's PFAS. It's really hard to remove. It's barely hydrophobic. And PFOS is one of the most hydrophobic of the PFAS. So I have the target effluent concentration, and then it computes the media filter lifetime. So you can see the regenerated activated carbon obviously lasts more than doubly long. That's a big plus, right? The chemical removal performance is going to run for a couple decades. And there's some estimation or quantification of the uncertainty of that lifetime. And then there's the cost associated with it for different suppliers' estimates that we've pulled together. So it allows you to say, like, am I willing to save $13,000, but have to replace it twice as frequently? That's nice cost benefit calculus for a project builder owner. Here's another scenario where we said, okay, well, what if we normalize the performance for GAC and biochar and regenerated carbon? What if we say, okay, we want both of them to achieve 40% removal. So I've now lowered my removal target, and I'm going to do that. I'm going to have a longer HRT, just the scenario that I ran. So I've got a retention time that's almost 3 hours. So that's really long. I think that's beyond practical. But what you see is, I say, if I do biochar, which is, everybody knows, cheaper, that's why there's so much talk about biochar, but I need to have 25% by volume in the media filter be biochar. That's now a bigger number. And so you see, with 5% by volume, I can get the equivalent removal using a regenerated activated carbon. And so now the cost just became equal. So keep that in mind, that some biochar isn't this magical substrate that you can or amendment that you can add that is so much cheaper than carbon. Well, you may need less carbon to be equivalent to the amount of removal you could get from the biochar. So this is all based on the MIDI-COM studies in the lab at Stanford. So yeah, that's all I have on the tool, and I'm happy to open it up for questions now. That's a good question. Well, filter sand is a really nice substrate because it allows physical removal of particulates, and it allows a little bit of hydraulic control, so that you have kind of a steady flow through the media mixture. It's also, these are expensive amendments compared to filter sand, and so that's why you see these kind of infrequently used. I think with any media filtration device, what you're really trying to do is balance out the longevity based on the two modes of failure. One is clogging and one is chemical breakthrough. And I will say that up until 5 years ago, in all of our work, we do a lot of work with Bob Pitt, and studied longevity and published on longevity of media. And I've never seen breakthrough as defined. No, breakthrough is a term that's often thrown around. There's breakthrough on day one, right? There's a measurable effluent concentration. That's not what I'm talking about. I'm talking about breakthrough in the sense of effluent concentration starting to change, or removal rates starting to change. That is the trigger for potential media replacement. And what I was saying was, for the first time in my 25-year consulting career, this is the first pollutant I've ever seen to break through. Now, some of the sites that I'm treating are generally cleaner sites. I work with a lot of industrial sites. And so we see that clogging at all of them precede breakthrough. PFAS is the first one where I have a site, I didn't show you the slides, but I have downspout filters at a PFAS manufacturing site. The influent concentrations are above 10,000 concentrations, which is the same influent concentration that I showed in the GAC slide. And that one, breakthrough, was in the second storm. I have never seen a chemical like that in my career. Think about that. In the second storm, it was PFOA. That's crazy. It's not an effective remedial strategy, right? Yeah, and that's true when you have high influent loading and you have a chemical like this. In California right now, all NIPD's permits are basically on pause. All renewals are on pause because they have to consider the implications of the Supreme Court decision that invalidates the end result receiving water limits. And so they're trying to figure out how to do that. And there's a lot of discussion amongst, I'm a chemical engineer. I serve as expert, testifying expert to attorneys. I'm not an attorney. But what we're seeing in the cases that we're working on is that there's a lot of industry groups trying to advocate for how they'd like to see the replacement occur. And we see the permit writers working with their councils, how they are thinking. And the initial things that I'm seeing in the first batch of released revised permits are that where there's an abundance of WQ bells, like in municipal wastewater permits, they're a little bit more comfortable from just deleting the receiving water limit language. But in those that don't have that, which is all stormwater permits or all general stormwater permits, there's less comfort by losing that protection. And so now there's like a soul searching happening. Does that mean more use of WQ bells? Does that mean more prescriptive BMP based compliance to the MEP? So they're trying to work that out. And meanwhile, organizations like CASQA and whatever the Washington alternative is, they're trying to figure out what should they be advocating for in those permits. And this has really important implications for some of the ongoing cases around this that are just a little bit behind San Francisco. And I'm working on some of those, and their court decisions just came out about the enforceability of the language that remains in there for MS4s. And I think the decision that came out last week was that it is still enforceable despite the SCOTUS decision. So that's why I'm saying there's kind of a lot of uncertainty as to where that's going to head. So I'm not a process engineer. I work with process engineers. So I'll tell you what they say on this. In our active treatment systems, there has been questions about reactivating the carbon instead of just removing it and disposing it. And in every instance that I've seen so far, especially all those that involve stormwater, they've always said it's better to just dispose. It's cheaper to just dispose of it than to try and reactivate. You obviously can't destroy it unless you're cooking it, which comes at high expense. I have one example where we have a subsidiary, Savron, that does a thermal destruction of PFAS, heating it at in smoldering temperature. Mm-hmm. But like that just, the costs don't pencil out for bringing that technology to the site, taking the GAC out of the vessel, cooking it, putting it back in. It's so much cheaper. And we live in a disposable culture. Mm-hmm. Everything, we just throw it out and build a new one. It's cheaper that way. Unfortunately, it's less sustainable. Mm-hmm. But cost-wise, you just get rid of it. I appreciate that. A bottom line question. I love that. I would say that, endorse or advocate for source control legislation that elected officials are pushing for so that you get it out of the environment, at its source. And then I would say maybe in certain high sensitive project scenarios, like if you have a dry well at regional scale, pushing water up gradient of drinking water, municipal drinking water well, or even private municipal wells, you may consider more robust pretreatment ahead of the dry well, where you're incorporating higher levels of GAC in a media filter context. Don't just, in that scenario, don't just build a standard dry well with a sump or a hydrodynamic separator in front of it, because you're not going to mitigate the PFAS loading into that. And I would say, like, if you're not going to do it for human health reasons, do it for risk mitigation perspectives, because there are so many lawsuits over drinking water contamination of PFAS right now and cost apportionment to so many numbers of parties. If I was a municipal agency owning a green infrastructure asset, I don't want to be one of those. Leave it to the PFAS manufacturers and to the AFFF users. Like don't get added to that PRP mix.